thanks so much for the invitation. So I never had the pleasure of being a postdoc at Perimeter, though I have visited several times and really enjoyed my time here. But now that I'm local at University of Toronto, my standard for travel is between University of Illinois, where I was previously in Fermilab, which is a 2.5-hour drive that I've made round trip in one day many times. And so this is now like, a factor of 2 less. So I expect to be hanging out here a whole lot if you'll have me. And so I figured I would take a little bit of kind of a retrospective look at particle physics and cosmology, given the theme of the workshop. So 25 years ago, I was a freshman in high school, reading books like The Elegant Universe to learn what all the awesome stuff in physics was. And thinking about what was happening 25 years ago, plus or minus 5 years, we just found the top quark. That things like that, definitely made headline articles on the front page of the New York Times. We had this amazing collider called the LHC that was soon going to turn on and discover supersymmetry, and where there's going to be so much new physics that we wouldn't even know what to do with ourselves. And then on the cosmological front, as we'd heard about from the talks on the first day, we just discovered dark energy. WMAP was about to launch, so this beautiful picture from the first run of WMAP was from 2003. And this was obviously the most exciting thing to do. I thought about going into aeronautical engineering, I think, when I was in high school, but was convinced that all the cool airplanes were actually just designed 20 years before they ever went into service. And so if you wanted to do anything cutting edge, it really needed to be physics. So I was convinced. And though now I think okay, I guess I could have been working at SpaceX. That would have been pretty cool. Anyway, okay, so what do we do as physicists? So we go where the data leads us, and there's just been an enormous amount of data over the past almost century, convincing us that most of the universe is not made of baryonic matter. And so, by the time I got to grad school, I decided that the thing that I felt like I could make the most progress on was trying to understand what dark matter is. I'm sure you've all seen plots like this. We have evidence for dark matter coming all the way back from the CMB. We have n-body simulations showing that dark matter is the gravitational scaffolding for galaxies. So, we wouldn't be here today if it weren't for dark matter. Of course, galaxy rotation curves, kind of the oldest set of evidence, but now just kind of coming in droves. And so I think dark matter is a great place to start looking for new physics, and that's where I've been spending kind of most of my time trying to figure out what else might be out there. So again, I thought I'd take a look at what we knew about dark matter 25 years ago and what we know about it now. So I checked. So this is from Bernard Satellet's Review of Modern Physics article from 1999. That's the parameter space for WIMP dark matter. You'll see here the cross-section of 10 to the minus 41 that was the best that we'd excluded is now basically off the top of the plot. So 25 years later, this is from SNOMAS 2021. Also kind of terrifying that SNOMAS was already 3 years ago. I don't know where the time has gone. But really, we are delving deep in the mantra of the SNOMAS process, really pushing down in cross sections as far as we possibly can, down to the neutrino fog. Also, I was amused to see that axion dark matter did make an appearance also in this review from 1999. The mass range that was probed was from, let's see, I see, this is just a projection at the time. So the mass range that was probed was from 9 to 10 micro EV, and that was it. And now we see Kieran O'Hara's beautiful axion plotting tool that's covering 19 orders of magnitude of possible axion masses. And so this is the second part of this no-mass mantra, so delve deep and search wide. So what have we learned about dark matter? We haven't found it yet, but of the things that we're still looking for, we have really decided as a community to widen our priors. And I think this is important, and that transition, I think, was happening, at least for me, kind of between grad school and my first postdoc, that one really needs to kind of keep an open mind for where dark matter might be. And then I learned how to make plots like this from people like Mina and Surjit Rajendran, that really, if we widen our priors, where are the just observational endpoints on dark matter? When I started showing this plot, that number down there was 10 minus 22 eV, but thanks to Neil, I've now changed it to 10 minus 19 eV, and I'm always embarrassed when I forget to change it and then remind myself that Neil has the best limits on fuzzy dark matter. Okay, but at the low end, dark matter needs to fit inside a galaxy, or it's not meaningfully gravitationally bound in any sense. If you want it to be an elementary particle, of course, the highest scale that we know how to talk about is the Planck scale. But you could really extend this another 50 orders of magnitude to the right if you want dark matter to be, or at least a subcomponent to be primordial black holes. That's all fine. And we really just don't know, based only on sort of observational evidence, where dark matter might be. So it's worth thinking of all the different kinds of experiments that we can to try to probe as many of these regimes as we can. So it kind of falls naturally into at least two regimes. So if dark matter is much lighter than an EV, occupation number is large. We call that wave-like dark matter. Okay, you could say it behaves like a classical field because it has large occupation number, but you could also talk about its quantum statistics, and a lot of people have been doing work on that front. But the point is that there's a lot of dark matter. The individual kinetic energy carried by any particle is negligible, but just like we're not worried that the individual energy carried by a microwave photon can't be detected, you can listen to things on the radio, you can pick up your cell phone because many, many photons all acting at the same time gives a macroscopic displacement to some antenna in your phone. Dark matter could be doing the same thing. Dark matter that maybe the canonical WIMP range is from about a GeV to about 100 TeV, but you can imagine pushing that down lower. There, the number of dark matter particles per unit of phase space is small, but they carry some amount of kinetic energy one at a time, and then you're really looking for rare collisions. And the game is, because the kinetic energy is proportional to the dark matter mass, the lighter the dark matter, the less kinetic energy, you need to be looking at sensors with lower and lower thresholds. But what I hope is clear is that at least this 50 plus orders of magnitude, there is no one-size-fits-all solution for dark matter direct detection. And so what I want to tell you about is a bunch of different interdisciplinary collaborations that I've found myself part of or sort of dived headfirst into that has been a lot of fun, talking to people from different fields that particle physics canonically doesn't necessarily associate with, in an effort to detect dark matter across these different mass ranges. So when I describe the way that I tend to think about dark matter is you can ask all these kinds of questions that we don't know the answers to. What is the mass of a dark matter particle? Does it have any non-gravitational interactions? How is it made in the early universe? And at least one way of approaching things is you guess some answers. So these tend to go by some viable benchmark models, like you write down a particle physics model that describes, for example, the way that it would annihilate in the early universe to make sure that you get the correct relic abundance. And then you turn that diagram around and say, well, that implies there must be some interaction with standard model particles. And then you can use that to ask, how can we detect this dark matter on Earth? Of course, it's also important to try to find signatures of dark matter in astrophysics, but at least in a laboratory environment, you have some modicum of control over the medium in which you're detecting it, and so that you can maybe hope to control the environment a little bit better. And the way that I've approached this problem is using particle physics. That's where these benchmark models come from, plus condensed matter, quantum chemistry, material science, quantum sensing, even as I'll show you electrical engineering, to try to understand dark matter interactions in terrestrial detectors. And so I think it's been nice because I think historically particle physicists were kind of everything physicists. Done a lot of reading about the history of particle physics. Like Hans Bethe during the war was calculating cavity perturbation theory in order to figure out how to make better microwaves for radar. Also calculating impacts of projectiles on tanks to try to have like stability of the armor on tanks and stuff. And you never know how many of these weird things led to the amazing advances in theoretical physics, like the Lamb shift, microwave technology, radar. So I think it's worth keeping an open mind and just kind of going wherever the fun physics is, even if it's not what you originally thought that you were doing. And I'll give you some examples that, at least for me, this is not what I thought that I would be doing when I started my PhD in physics. So the first point that I want to make is that if you're looking for dark matter that's lighter than about a GeV, condensed matter physics is not optional, but it's mandatory. So you can kind of think of this like, can you treat your detector like a bag of free particles? In particle physics, we're used to colliding, one particle at a time, maybe a large hadron collider. So maybe this is like, playing pool. I have to make the pool reference because Gordon is here. But if you ask a condensed matter physicist, how they think about interactions, they might think more like, you throw a pool ball into this ball pit, right? Everything kind of moves around at once. There's lots of collective effects that are important. And it turns out that in this case, as the dark matter gets lighter, you start running into more and more scales that are characteristic of your detector system. So if the kinetic energy of the dark matter is about 10 eV, that happens to a mass of 10 MeV, that's comparable to atomic binding energies. In order of magnitude lighter, that's comparable to band gaps in semiconductors. Order of magnitude lighter optical phonon energies. And then, of course, if the dark matter gets really, really light, it's coherent over your entire detector. And so you really can't treat your detectors made up of like a bag of free electrons. You have to ask about what is the condensed matter physics of your detector, and how does it affect the observables that you're looking for. So another lesson that I learned is it's important to ask the right questions if you want to get the right answers. So if you were a particle physicist and you wanted to calculate the probability of dark matter doing something in your detector, you might start by writing down some matrix element. And then, of course, the matrix element, there's some scattering operator that looks like this in momentum space. And the first question you might ask are, OK, well, what are the wave functions of my system? But actually, from the condensed matter perspective, this picture of a single atom with a bunch of electrons is not the way that condensed matter physicists would think about a semiconductor. There's all kinds of interesting collective effects. And maybe I want to be agnostic and just say, like, OK, I just want to know what is the object that tells me if I kick this system with momentum q and energy omega, what is the probability that something happens? That has a name in condensed matter physics. It's known as the dynamic structure factor. And it turns out the right question is not what are the wave functions, because I can't even write them down in some sort of analytic way. But this function, it turns out, is measurable, at least in some contexts. And there are codes that exist to calculate it that don't require you to back out the intermediate steps of these wave functions, I and F, that I might not even know how to characterize because they're complicated many-body things. So knowing that this is the observable that we actually want actually leads to nice ways to calibrate detectors to leverage all the work that's been done in condensed matter physics in understanding dynamic response functions of semiconductors and also more exotic materials. And it kind of took the community maybe like between 5 and 10 years to understand that looking at the system the way a condensed matter physicist would is actually the better way to understand how your detector is actually going to respond to dark matter. OK, so just an aside about me. So in grad school, I wrote a textbook preparing students for the physics GRE, and I knew so little about condensed matter physics that I had to contract out the section on condensed matter to another grad student. And so little did I know that this was going to be the bulk of my work as a postdoc. And so this is example one of many of, never prejudice yourself to saying you're only going to work on thing X, because thing Y might end up creeping in and be the thing that actually determines a lot of your career. OK, so I've had the good fortune of being able to go from this theoretical understanding of calculating dark matter interaction rates in terms of a response function to an actual collaboration with condensed matter physicists and material scientists at Fermilab, SLAC, and Los Alamos to help develop a prototype detector made of these narrow gap materials. So if you're looking for dark matter that's lighter than an MeV or so, you need a material whose band gap is smaller than an EV. These are pretty exotic materials that's pretty finely tuned. There's a material science group at Los Alamos that has developed expertise in developing these very clean, high resistivity materials that have a very clean band gap that we can then hope can look for dark matter that's lighter than an MeV. And the theoretical work here is understanding how if dark matter interacts through some mediator that couples the charge density, then indeed the thing that determines the dark matter scattering cross-section is this dynamic structure factor that you can actually go and measure in electron beam experiments done by my colleagues at my former institution, University of Illinois, but also compute using tools like density functional theory. So this has been a lot of fun, and hopefully some version of the detector might end up in SNOLAB in the somewhat near future. OK, so and yeah, I'm going to give you a bunch of examples here without going into too much detail in any of them, but if people are curious, please feel free to ask me after. The next kind of interesting intersection of fields came from quantum chemistry, and this was very unexpected. This came out of like a random conversation that I had with Juan Collar when I was at the University of Chicago, who came up to me in the kitchen and was like, "Yoni, I've got a vat of benzene. Can we look for dark matter with it?" I'm like, that's a cool question. I wonder. Started looking at some old textbooks on the physics of organic molecules. But the story basically is that carbon likes to form molecules that are planar. And when they're planar, that means there's a strong anisotropy, right? These things are not rotationally symmetric. There's in-plane and out-of-plane directions. And so the electrons are bonded in such a way that the electron orbitals, where the electrons transition, stick out of the plane of the molecule. And so you can imagine dark matter scattering one of those electrons to an excited state that then de-excites and emits a scintillation photon. But that scattering is anisotropic. It depends on the momentum transfer of the dark matter to the electron in your material. And it turns out this actually can give you a daily modulation of the dark matter scattering rate, which is something that no detector has the capability of doing so far. If you're in a big, if you're looking for like GeV scale dark matter, trying to look for daily modulation requires you to track the direction of the outgoing excitation, which means you need a very dilute medium, like a gaseous target. But here, the direction of the emitted scintillation photon is isotropic. It's the scattering probability that's anisotropic. And that's a thing that tends to happen very often in these molecular systems for lighter dark matter. This doesn't work for a vat of benzene because the liquid molecules are all oriented randomly. But there's a cousin of that molecule called transstilbene that likes to form solid crystals, where you do get something on the order of 20% expected daily modulation. So some colleagues of mine at University of Chicago and Fermilab wrote a paper proposing this. And then we got some chemists excited. And so now I just get to like show you some cool pictures of experimental things are happening just to demonstrate that like, yes, some theorists can be like, hey, wouldn't it be cool if you did X? And then people can actually go and do it. It's amazing. So the first thing is like, you can get crystals of this transstilbene stuff that weigh 26 grams. Like that's like one honking chunk of crystal. So you can actually get a macroscopic mass of these materials. This is not some like super esoteric thing. They showed that if you shine UV light on these crystals, you can actually detect the scintillation light that comes out with a CCD. That shoulder right there is the signal above the background. You can calibrate your detector by firing electrons at your organic crystal and looking for the probability of a scintillation photon being emitted to be dependent on the angle of the electron beam with respect to your crystal. Those measurements are now are in progress, but we're hoping this is again going to be some sort of prototype detector that could be used to detect dark matter in the MeV to GeV range with the added benefit of a fairly large daily modulation.
Do we know what the big hump is at the background?
This is the lamp. So basically, they shine a UV lamp on the crystal. It absorbs UV photons and re-radiates them, and some of that lamp gets through. But this is exactly the emission wavelength that you can see from the previous slide. It's emitting exactly right here where you expect it to. Yeah. OK. So then moving on to much lighter dark matter. So this is the particle physics plus electrical engineering section. So if you have ultralight dark matter like an axion, so this thing is like some sort of field that you heard from Roni's talk, suffusing your entire laboratory, oscillating at an unknown frequency. If it couples to photons, you can think of it as some sort of an effective current. And I remember the day that we drew this cartoon on Jesse Thaler's blackboard at MIT, realizing like, oh, trying to figure out the signal from axions is literally like an undergraduate E&M problem of like you're just using like Ampere's law and the right-hand rule and everything. But then if you want to read that thing out, okay, now you have to like care about like how you take some flux from the inside of this this toroid and like couple it into some squid. So I had to call up my experimentalist colleague, like, what's a squid and how does it work? And we drew these like very cartoonish circuit diagrams in this paper. And then amazingly, again, some experimentalists at MIT got really excited about doing this. And from 2016 to 2021, so 5 years later, we actually had leading limits on the axion photon coupling from a design that looks very much like the cartoon that we had originally drawn. The circuit diagrams have gotten considerably more complicated. But this is one of these things where the actual work involved, the commissioned a company that's used to making magnets for like fusion startups to wind this magnet here. You put something in a fridge that already existed because there are other reasons to have ultra cold dilution refrigerators hanging around MIT. And at the end of the day, you can actually take a measurement that right now, okay, it's only a little bit below the existing astrophysical limits on the axion photon coupling, but maybe in its larger implementation might be able to discover this kind of axion dark matter.
You did the comparison between expected and offset, the blue is offset?
So let's see. So the blue is the first run of the experiment. the green, these Brazil bands are the second run of the experiment. The point is the limit's improved. And so whether they dip below the CAS limit depends on like some careful statistics about what the 1 and 2 sigma containment intervals are. But the point is, in principle, it works. And like the way that you get this thing better is just scaling it up, which is the idea of the DM radio collaboration, which is if you actually want to be able to dip very deep into this parameter space, you need to actually take into account the fact that these inductors, when operating at very low temperatures, are in fact quantum systems. You need to care about how quantum limited your squid is and the relation between back action noise and imprecision noise. And this plot I just find amazing because this is a bunch of particle theorists running COMSOL, which is the standard suite of software for simulating electrical responses in very complicated systems. And this is what we needed to do to really understand how a detector like this would behave when the frequency of the dark matter is comparable to the light crossing time of the detector, which is like the annoying regime where the quasi-static approximation from undergrad E&M doesn't really work anymore. You just have to calculate the thing numerically. But if you really want to know what the sensitivity is, you have to do that. And again, I just want to point out, like, my worst class in college, Tim, this is Dave Buchholz's class, was electronics lab. And I was so bad at this class that it was what convinced me that it was the right thing to do to go into theory as opposed to experiment. I was sure that I would never end up doing this. Again, when I wrote the GRE book, I outsourced the E&M section to my colleague Adam Anderson, who works on SPT and is the one who taught me about squids. This is not what I thought I'd be doing as a particle physicist, but it's been a lot of fun to be able to come back to this stuff and really be able to put all of this really good physics to use in service of trying to detect dark matter. Sorry? Yeah, I mean, so like the other joke that I make is like I definitely don't want to be the one turning the knobs, but it's a lot of fun to ask people to turn knobs and then have them actually do it and see what and see what happens. Okay, so now I want to shift gears a little bit and talk about something that I've kind of been pivoting into recently. Is so where else might data be leading us? We've looked for dark matter. We haven't seen it yet. We have not covered the full parameter space, and so continuing to look there is incredibly important. But you know, Renee had mentioned that particle physicists like setting limits. Well, we also like looking for interesting unexplained phenomena in the data and seeing if we can explain them. You might have heard of this thing that's been happening recently called machine learning and AI. Anybody who's serious will admit that nobody understands how these very complicated systems work from first principles. So you might have seen this XKCD cartoon. This is your machine learning system. Yep, you just pour the data into this big pile of linear algebra and then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right, right? So as physicists, this is a very unsatisfactory explanation of a very complicated system that nonetheless exhibits very striking regularities. So these are known as scaling law plots. This plot is literally not worth, it's not a picture worth 1,000 words, it's a picture worth $1 billion. Because the fact that you can confidently predict how much better your model will do as you throw more and more parameters at it was literally what launched the founding of the AI startup Anthropic and let OpenAI go from GPT-3 to GPT-4, and lo and behold, it sits right on that curve. So that's a phenomenon that, you know, it was physicists who had the idea of, hey, what if we did this thing on a log-log plot? But also, it's like, it means there's some interesting structure in the system that would be worth our time to try to understand. And if really data is king, if it's all about having the most data in the world, well, if we kept every single byte of data from the raw LHC collisions, we would have orders of magnitude more data than literally anything else in the world. So if we're really asking, you know, where is big data coming from? It's coming from physics. But it's not just random data. It's not like random pictures of cats. We understand it. We understand the microphysics. We understand the particle physics of at least, you know, up to some order in perturbation theory of things that are happening at the LHC. And as I showed with some colleagues, one of whom is now at Anthropic, you see these same kind of scaling laws when you train machine learning models on, say, simulated jet data as you do for data in the wild, which means that maybe we'll be able to use physics data, which we understand pretty well, to understand AI better. And then if we do that, we can turn that around and use AI to understand physics better. I think this is a very virtuous cycle. And so just in the last couple of slides, I want to convince you that I think this is a direction that's worth devoting some thinking cycles to. So this is a tagline I call HEP for AI for HEP. So empirically, it's been seen that AI works best on data, which is mostly low-dimensional, kind of dressed by high-dimensional fluff. So like here is an AI model where if you give it a prompt in words, an astronaut riding a horse, and I borrowed this very nice example from Alessandro Favero, who gave a talk here at a workshop back in April, it generates this amazing picture. But like, it doesn't really do it like pixel by pixel. Really, it's composing a bunch of features. So an astronaut is like a helmet plus a body, and then a horse is a head plus legs plus a body. And when you put these low-level features together, each of which are intrinsically low-dimensional, but of course, you zoom in, you see lots of different things. But it's low-dimensional stuff dressed by some high-dimensional fluff. So to a particle physicist, that sounds exactly like what's happening, at least for the strong interactions, where at parton level, the manifold of two parton events is two-dimensional. But then partons make more partons because the strong force gets stronger. You spit off more and more soft particles. You dress that event with some high-dimensional fluff. But unlike the probability distribution of images, I can actually calculate things about the probability distribution of particle physics events because I know that QCD works, again, at least at the sum order and perturbation theory. So if we understand what the machine is trained on physics data, maybe we can understand the physics better, but then also understand some general principles about how AI learns from natural data. So I think this is a nice cartoon that illustrates why like physics data is a really interesting intermediate kind of realistic data set. So again, you might have seen this cartoon. This is fields arranged by purity. Sociology is just applied psychology, just applied biology, just applied chemistry. The physicists go, which is just applied physics. Here it says, nice to be on top, but like, let's cross that out. Let's not be jerks. We're being interdisciplinary. And then the mathematician goes, oh, hey, I didn't see you guys all the way over there. And really, this is kind of the two poles of people studying machine learning. You can either literally ask what happens to a large language model trained on the English language. I don't know how to write down P of English. The best that we have is whatever a large language model predicts for us that P of English is. On the other hand, Gaussian data is very easy to analyze. So you can say, let me imagine that my data is literally determined by some covariance and some fixed covariance matrix that I put in ahead of time. You can do linear regression on that and learn some things. But I think physics data sits right in the middle. And again, to give you that at a little bit more of a technical level, so think back to n-particle phase space. So it turns out topologically that's a sphere. But if I have massless particles, a zero energy particle might as well not be there. So I can go from a higher dimensional manifold to a lower dimensional manifold by taking the energy of a particle to 0. Or I can get back to the higher dimensional one if I split a particle into two exactly collinear ones. That's indistinguishable, at least in perturbation theory, from just having that one particle there in the first place. So that means that actually, so how many particles is not a well-defined observable and perturbative QFT. That's just an interesting fact. But it means that our data has this really rich geometric structure that if you're just trying to come up with a toy model of data just on your own, I don't think you ever would have come up with something kind of this crazy. Like phase space is a series of nested topological spheres is like the kind of like really rich data geometry that like, an applied machine learning scientist might salivate over. But it's not just some random manifold. You can compute matrix elements, which are just probability distributions on phase space, to some, order in the strong coupling constant if you're doing jet physics. And you can compute some observables on the full manifold, which is an arbitrary number of particles, as long as they satisfy these conditions of infrared and collinear safety. So I think this is an underappreciated fact that like physics data has this actually really rich geometric structure. It's not just that we have a lot of it, is that there's something really nice mathematically about it. There's some non-trivial distributions, and I think it's an excellent benchmark for real data. And so just as like kind of a fun thing, I can show you this is what happens if you do a diffusion process on three-particle phase space projected to the Dalitz plane. It doesn't really matter. The point is a lot of these image models are trained basically by adding random noise to data and then trying to reverse the process. Here, adding random noise means moving in a random direction on phase space, but we're doing everything on a manifold that we know the event lives on, unlike, for example, the set of cat pictures where I have no idea what manifold that actually describes that. So I think we should leverage our knowledge of physics. We shouldn't just throw machine learning tools at physics. We should understand our data, use that to understand machine learning better. And I think a lot of people in the room have the expertise to really do that as well. It's not anything like I got convinced to come into this field by friends of mine who were doing this several years before. But I think that like there's a lot of really low-hanging fruit, and it's been fun to play with. Okay, so just to wrap up, so what might the next 25 years of particle physics look like? So obviously, we're going to go wherever the data is. We've heard a lot of amazing talks on all the data from LIGO. So there's all the Gaia data. Stellar astrophysics, gamma rays, fast radio bursts. Hopefully in my lifetime we'll see another collider. If that were a muon collider, I think that would be awesome. There's a lot of physics to learn there. There's amazing stuff that one could do with precision measurement. You heard some of that from Roni's talk. And these things are all going to happen. But I do want to make the point that progress in AI is orders of magnitude faster than progress in traditional particle physics, at least at the present time. And experiment, by which I mean just the fact that you can just type a natural language thing into ChatGPT and it can do your graduate quantum mechanics problems, like that is an unexplained phenomenon that is far, far ahead of any theoretical understanding. And so if we can use any of our toolbox in physics to make progress in that field, now is the time. This stuff is all going to be there. And I think at least at the present time, this is sort of where I think it's really interesting to focus a lot of energy. So happy to stop here and take a few questions.
Just want to understand. I didn't get the sign right. So OpenAI, for example, or Anthropic, are they using LHC data to train their things, or
Nope.
you're telling them to do it?
So I don't think that we should hand our data to OpenAI and Anthropic. The point here is they made their model X times bigger, and their performance improved exactly as they predicted. They don't understand why. This is just an empirical phenomenon. But if we understand, for example, where does this slope come from? If you can predict the slope of the scaling law from a property of the data, then you can figure out, can you change that slope? If you can bend that slope down, you've made yourself billions of dollars because now it's orders of magnitude cheaper to train a model that can do the same. But if that's just an intrinsic property of the data, not the model that you're using, then there's nothing you can do about it. So what I'm proposing is if we can understand, for example, where the slope of these scaling laws comes from on physics data, we can then at least use that as like a test bed to dash theories of AI against the rocks of data that we actually understand.
Sabrina? So just to make sure I understood the question, you're saying that because we have a lot of data, but it's very highly structured versus
Yes.
other situations, there's less data, but there's some nuances that's going to change the scaling law you would anticipate?
Well, I mean, so these scaling laws are only impressive if they extend for many, many, many orders of magnitude. And the point is we're just not going to be data limited in physics.
Sure, but I guess what I'm saying is that I don't know if I would expect the same scaling laws if there was only a little bit of things defined, right? If you
Well, I don't know. That's a question of like, what do you mean by how complex the data is? Is physics data simpler or more complicated than English? I don't know. We don't have those answers yet, but I think it's worth investigating.
Ronnie?
Yeah.
Can you, so I'm trying to pinch and zoom into that.
Yeah.
The plots with Q top versus QCD gens. So,
Yeah.
So this is not a cross section of the
No. This is the loss of a classifier trying to distinguish these two classes of events as a function of the size of the training set. And these are two different ways of pre-processing your data that give two different scaling laws. So the point of this plot is like, it can't just be the intrinsic geometry of the data. It has to be something about how that data is embedded into a nice space. And in physics, we know nice spaces to embed our data in that maybe we don't in language. Like language is embedded in random high-dimensional vectors that the machine learns. So this structure, I think, is worth really digging into.